the evidence is for that what's called the standard model of particle physics, which is both the players in the game, the constituents, the basic building blocks, and the force-carrying particles. And it's also a description for the mathematical theory which underlies them, which is a quantum field theory. We're not going to do the quantum field theory, but we're going to talk about what the constituents are, how they interact with one another, and we're going to produce some of the evidence for that. Now, hopefully all this will not be completely unfamiliar to you. So, the general topic is quantum physics. And the standard model. And that will be, as I say, the topic for the remainder of the course. And the main topic of today will be to introduce some of the players, the quarks, so-called quarks, and the leptons. We'll go and describe what those words mean. So as I said at the beginning, these are the smallest. As far as we are aware, fundamental, i.e. nothing smaller than them exists. Constituents, and these are the matter-like particles. So they are part of the constituents of the standard model of particle physics. The others are the force-carrying particles. Which we will do next. Or later. Not during this lecture, but in this future lecture. So we're going to introduce these and describe them a little bit. This will not be a historical overview of the discovery of those particles. This will not give you all of the insights into how they came about and all of the experimental evidence for them. Though that is a very interesting story. Part of that story you will be able to find in any standard particle physics textbook, of which I really hope that you have a copy at hand. My favourite for this course is Griffiths, which is on the reading list, and if you don't have a copy of a particle physics textbook, then make sure you do get one. Griffiths is probably the most appropriate book for the rest of this course, but others are fine as well. So we're not talking about the force-carrying particles here, we're talking about the matter ones. There is a possibility. Who actually would be interested in finding about how they were all discovered and the experiments from which they were discovered? Do you care? Is this where I have had a sort of vague offer from Professor Frank Close, who's the guy who wrote that book, and he works in the theory department, that if you want him to, he's offered to come and give a sort of 45-minute talk in Trinity term about how you find out how all these things were discovered, where they came from, and how you can discover them yourself and win your Nobel Prize. Is that filling with enthusiasm or not? Hands up if you like that idea. That's enough people, that's a little bit more. Okay, we'll try and schedule that again. Okay, fine. So we'll investigate that. For the moment, we're just going to introduce them and give some of the evidence. So what are the properties of these particles? So as far as we are aware, they are point-like, which means that they have no resolvable size whatsoever. Maybe that's a bit of an exaggeration because we haven't been able to resolve any size, but that doesn't mean that they can't have any. So the size, if they have got some size, must be less than or approximately equal to 10 to the minus 19 of a meter or so. And some of these you've met before, these fundamental smallest hadron-like particles. In fact, probably some of you will have met them even at school. So examples. We've already met the electron. We have met the electron lots of times before. We've met the electron neutrino. So these neutrinos are the weakly interacting particles, the ones which have a very small cross section with matter. All of the standard model matter particles they're fermions, and they all have spin half. Or spin quantum number over half. So we know that's true for the electron, and we may or may not know it's true for the neutrino. It's true for all of the matter particles inside the standard model. It's worth asking ourselves whether the other constituents of atoms or nuclei that we're aware of might also be fundamental constituents. So we can ask, what about the proton or the neutron? The answer, as many of you will be aware, is that these are not point-like. And they do have substructure. You know they're not point-like, so the radius of the proton is of the order of 1 femtometer or so. You can just work that out from scattering theory, from form factors, from the sorts of things we've been doing at the beginning and middle part of the course. It's not really part of the course, but I just mentioned in passing that magnetic moments these are spin-half particles, and there is a theory, it's called the Dirac theory, for how much magnetic moment you should have for every fundamental spin-half particle. And the magnetic moments of the proton and the neutron do not agree with the Dirac theory. The magnetic moments are not equal to those proposed by, or those suggested by the Dirac theory for fundamental spin-half particles. There's another further piece of evidence. And there are other pieces of evidence as well. Now, if we're attempting to convince ourselves that there is substructure within a proton, then one of the ways that we might try to convince ourselves of that is to try and knock the constituents out of the proton. Very natural thing to do. We convinced ourselves that nuclei were made out of protons and neutrons, partly because we can bang things into them and knock the protons and the neutrons out of them. So, we want to be able to ask the question, is it possible for us to fire in a high-energy projectile and knock some of the substructure out of these protons? This process has got a special name. It's known as deep inelastic scattering. Scattering should be obvious. Inelastic means that the objects at the end are not the same as the objects that you started with. You're knocking things out and creating new particles. And deep is a reference to the fact that this is looking deep inside the proton, and i.e. at very high energy, and very small wavelengths. You see that we're going to need wavelengths much smaller than the size of the proton to resolve its substructure, and energies much larger than the binding energies of the proton, of the constituents of the proton, in order to knock them out if they exist. And we can do this. And so clearly, if we've got some long wavelength probe, and we try and hit that against the proton, well, we've looked in the scattering theory part of the force, and we know that if we've got large lambda, a big wavelength, then proton looks or behaves to the projectile point-like. Whereas what we want to do is send in a small wavelength, high resolving probe that's much smaller than the size of the proton, and try and kick one of its constituents off. And in order to do this, we need small lambda and high E. We're going back to the accelerators that we talked about before. So we need lambda much less than the radius of the object, whereas here we have large lambda much larger than the radius of the object. Now, a series of experiments of this sort have been done. The most recent were done in Hamburg in an accelerator called, well, an orbit called DESY, an accelerator called HERA. Let's just write that down. So, deep inelastic scattering experiment. HERA accelerator. There's not really remember, it's just in case you want to find more information about it. The Deutsches Elektronensynchrotron, someone can speak German better than I can, lab in Hamburg. It's quite close to the world's biggest insect. If anyone happens to be in Hamburg, you can view those. So at this laboratory, what they've been doing, and it's been running over the last 10 years, when they shut down 2 years ago, is that you fire electrons around a beamline in one direction, you fire protons around in the other direction. So we send electrons around like so, protons around like so. You need two separate beamlines to do this, firing off each other, running in nearby rings. And what you observe is the following. What we have observed is the following. The electron comes in, it is deflected, and in being deflected, it exchanges a force-carrying particle, a photon, a virtual photon, with one of the